Awesome. So thank you. Hi, everyone. Just before we begin, we really wanted to extend our gratitude and thanks to the community, the organizers for having us today. So thank you. As mentioned, my name is Omri Shiv. I'm a senior open source ML engineer at AWS, and I'm here with Ajay today, Ajay Vohra, principal generative AI applied engineer also at AWS. And we're going to be talking about simplifying generative AI model training on Kubernetes using Helm charts. So our agenda today, we're going to start with talking about the generative AI training landscape, specifically on PyTorch. And what we've seen is that, there's multiple frameworks. Today, we're only going to talk about 4 of them, but there are certainly more than that. What we've seen is that some of them are opinionated, some of them are more generalized, some of them are domain specific, some of them are more generic. Some of them package a lot of functionality. Others require external libraries to give you a little more flexibility. And then there's differing levels of abstractions for that complexity. So as an AI engineer, as a data scientist, as an ML engineer, you might stick to one of them, or you might use more than one of them, depending on what it is you're trying to do. So how do we make deploying them easy so the data scientists and the engineers can focus on the model development while giving them flexibility in the framework choice? Next, we're going to speak about generative AI training in Kubeflow, again, specifically about PyTorch. How do we deploy, how do we package the code generally when we deploy the models for deployment? And then what are the challenges when it comes to reproducibility and deploying of that code? And then we'll get into the key ideas and the contributions, which are how do we ease this complexity of deploying the models, the diverse frameworks without sacrificing the functionality that's available within those frameworks. And then we'll go into a demo. So as we said, we'll be focusing specifically on some PyTorch frameworks. This is not an exhaustive list. The ideas here are going to be applying to anything that you can deploy on Kubernetes, not only specific to PyTorch. So just a forewarning, the next few slides are a little dense. We wanted to make sure that we had the information there, but we're just going to focus on the key takeaway for the presentation, and we'll share them out afterwards. So from a framework overview, what we've seen or what we focus on here are 4 frameworks: NeMo, PyTorch Lightning, Hugging Face Accelerate, and FairSeq 2. And so as an overview, NeMo and FairSeq 2 focus more on specific domains, NeMo being the generative AI domain, FairSeq 2 being sequence modeling, and then PyTorch Lightning, more of a general framework for deep learning, and Hugging Face, kind of a general framework for distributed computing. From a design perspective, what we've seen is that NeMo and FairSeq 2 abstract the domain-specific complexity, while Lightning and Accelerate kind of are more modular to give you that ability to go beyond and explore and extend the frameworks. From an interface perspective, we've seen 2 primary interfaces. Whether it's Pythonic or YAML, what we'll see is that we're actually able to use either interface to make deploying and using these frameworks in production are a little more easy. From a model support perspective, as we've said, NeMo is kind of more focused on the generative AI domain. So we see generative AI models there, FairSeq 2 being sequence models. So we see support for those sequence models there. And then PyTorch Lightning and Accelerate kind of either supporting all of the models that you can possibly use there. From scaling perspective, NeMo and FairSeq 2 have built-in support for scaling, whereas Lightning and Accelerate, you might need these external libraries for model scaling like FSDP or DeepSpeed. For fine-tuning, NeMo and FairSeq 2 have that built in. It's domain-specific support for the fine-tuning, whereas Lightning and Accelerate, again, need external libraries. For the training features, NeMo and FairSeq have that built-in support for their sort of domain-specific features. Lightning covers many of the use cases that you would need for general deep learning, and Accelerate, being more open-ended, requires you to either implement it yourself or use an external library to be able to do that. From a data processing perspective, NeMo and FairSeq 2 provides data processing out of the box with a kind of what we want to emphasize here is FairSeq 2 calls out the C++ streaming pipeline, which is going to be important in the next slide. Lightning and Accelerate requiring external libraries for the data processing for more of the extra functionality. And then here for the training operations, when you go to deploy your training into beyond your laptop to a cluster, NeMo provides supported containers from NVIDIA. Lightning and Accelerate provide community-supported containers. You can launch them on Kubernetes and Slurm. FairSeq 2, as we mentioned, with that C++ dependency, you have to build it yourself. And so if you're going to use FairSeq 2, you need to make sure that you're able to compile it for the target that you intend to run it on. That's very important when it comes to that. And there's no supported containers that you can just grab off the shelf. So we hope that this very quick introduction to frameworks has kind of highlighted our problem that we're trying to solve. And that's, we have a lot of these different frameworks. Some of them are specific to certain domains. Some of them are more generalized. So depending on the problem that you're trying to solve, you might use one and you might stick with it, or you might find that you kind of need to bounce back and forth from different frameworks. So this diversity creates complexity as we try and support the ability to deploy these into an environment for that. So then the question becomes, how do we simplify the use of these frameworks without sacrificing their native functionality? And for that, I'm going to turn it over to Ajay.
Thanks. Let me share my screen. Okay, so thanks, Omri. Now let's talk about generative AI training, specifically in Kubeflow. Again, even though the context today is PyTorch, please keep in mind all the ideas we discussed are equally applicable to other frameworks that we're not discussing in detail. So in the context of Gen AI training in PyTorch, our assumption for this talk is that we're interested in rapid innovation, and we want to be able to do iterative development with any of the Gen AI training frameworks that we may need for a given use case. And for simplicity, we want to use a consistent approach across all these frameworks, so it's easy to switch across them or different orchestration platforms, across the whole landscape. And that's sort of like the main thrust of the talk today. Okay, to make it concrete, let's focus on PyTorch. And within that context, let's assume we're using Kubeflow Trainer like PyTorch Job to do our training. So in this context, the stack will look something like this. You have, of course, the PyTorch job replicas, the pods that are actually doing the distributed training. And they could be doing it in an elastic setup or in a master-slave type of setup. And then at peer level with these pods are these daemon sets that basically provide access through the container storage interface drivers to the storage or to the underlying accelerators like GPUs, their discoverability, the access, and so on. And then, of course, underneath all of this are the nodes, the physical infrastructure on which the stack is running. And we assume that the nodes have been provisioned through something like a cluster autoscaler or a Karpenter and basically be provisioned on demand. So that's all like the assumed architecture in terms of the stack. So in this stack, where is the complexity? And so what we found is through working with numerous customers and experimentations, internal and external, is that most of the stuff that is at the node level or in the context of daemon sets or the foundational libraries, the communication libraries for collective communications, this is all handled fairly straightforward manner through things like Helm charts, things like Terraform, and this is very well standardized. And the complexity doesn't reside in these layers or in these components. Rather, the complexity resides in the training scripts and the configs, their variation that arises from all the different frameworks and their approaches, their design philosophies that we just discussed. So what are some of the ways to deal with this complexity that resides in training scripts and configs coming from different frameworks? Well, one idea is simply to essentially add the scripts and the configs themselves to the Docker container image. And this is, in fact, one of the things that's done most often. And this works, but the key challenge with this approach is that it slows down the iterative development. Because every time you make a code change, you have to now build images and push them. And then more importantly, at runtime on your nodes, they have to be pulled down again from the image repository. So this essentially slows down iterative development. Now, another idea, which essentially is that you don't put these training scripts and configs inside the containers, but rather you stage them at on some external volumes, and then you mount those volumes. This is, in fact, is universally done with Slurm, for example, and this can be done through persistent volume claims with Kubernetes, so with the Kubeflow operators. And the challenge with this is that this makes it very hard to manage because of these scripts and configs being externalized and not part of any the definition of an experiment or a run, and that makes the reproducibility of the training runs very difficult. So that's the key challenge with it. But it's essentially a good idea, so we're going to build on it and come to the key ideas that we are proposing to address these challenges and address the complexity. So our ideas can be actually very simply summarized as two key ideas. The first key idea is that we're proposing that the containers, the training scripts and the configs should be put into an executable config map. But the config map is not to be defined statically, but to be defined through templatization, like Go templatization, which means Helm charts. And the second idea is that everything that's going to be used in this context, all the Kubernetes APIs, so for example, the Kubeflow trainer, PyTorch job, NPI job, whatever it is that you're using, array job, whatever it is, we want to templatize it and then use it through Helm charts. So those are the two ideas that we are proposing. And we have used these two ideas successfully to work with all the frameworks that we have just discussed across hundreds of different examples. And that's what we're going to share next. So first of all, what is the structure of this executable config map that we are proposing that is so generalized that we can work across all these frameworks? And simply put, the structure is that you have a config map which allows you to first inject some sort of a Git repo so that you could clone it. And this is optional, of course. And then, of course, within that, specify a branch and a hash commit. And then, of course, you can also inject, in addition to the Git repo, you can inject inline scripts. So, for example, if you want to define inline scripts of Python, configuration files, or any arbitrary configuration files, you can do that. And then you can inject a pre-script, which is like a shell script that needs to be executed before your training job is launched. Then you can define that. And then you define whatever it is that your training command is and the arguments. And that basically is the launch command for your training job. And then finally, you can have a postscript to do cleanups or do other kind of things that you need to do after your job is completed. And these concepts apply the same way whether you're doing training or you're doing fine-tuning or you're doing data processing or you're doing pre-processing of the data and so on. The concept is the same. And now specifically, what do you do if you define this executable config map in the context of actually running, say, for example, PyTorch job? Essentially, what you do is you, of course, create a volume out of this config map, which is pretty straightforward. Make the volume such that the script in it is executable, as you see here. And then you mount this volume onto the container. And then that mounted script becomes your entry point for your PyTorch job replicas. And so they all have like a standardized entry point, which is this training script. And then the content of the training script determines what is actually going to happen. So that's the simple idea. Now, if you want to string this, we'll skip these couple of slides. They're not super important. We'll get to the next important thing, which is if you want to string things together into a pipeline, then how do you do that? So for that, we have defined a Kubeflow Pipeline component that can operate on a list of Helm chart configs. So think of it that each config that you pass in it is essentially definition of some Helm chart that you want to use, and also the values you want to use with that Helm chart. And then once you have that list, then basically this component executes through that list in a sequential way. And for each Helm chart that it finds in the list, it basically installs the Helm chart. And remember, this Helm chart is templatizing things like a PyTorch job, which has the config map and all that. And then it essentially installs the chart, waits for the pods to finish in the chart, which is sort of like your training job replicas, wait for them to finish. And then at the end, it uninstalls it. And then, of course, if you have a list, it's just going to go through sequentially and install them. And basically, once it reaches the end, meaning everything installed ran to completion successfully, it returns a success. If any of these components or any of the charts fail, then of course it returns a failure. So that's basically the Helm chart component. And that you can think of it as allows you to define a straight line DAG for a workflow. And of course, if all you need is a straight line DAG, then in the pipeline, all you have to do is just use this single Helm chart component as shown here. And that gives you a straight line workflow for whatever it is that you want to do. So that's basically the idea. To summarize again, you templatize everything, you create charts. These are not going to be large in number. They're usually less than 10 to work with lots of different things that are possible across training, across data processing, across inference. And then you basically drive these Helm charts through value files. And you can then use these Kubeflow pipelines if you want to string them together into a pipeline. Okay, now let's jump to a demonstration. So I'm going to stop sharing this and share a different screen. Okay, so let's start with a simple demonstration where we want to do training of something relatively very simple, which is we want to pre-train a bird type of model. And essentially, it's going to use some standardized data set like Blue MRPC. And how do we go about doing that? So first of all, the YAML file, or you can think of it as the values file that's going to be used with the Helm chart that goes with it, will look something like this. You define the image, you say how many GPUs you need, what node type you need, and so on. And then you define the things that we had talked about earlier. You say, where is your code, branch, hash commit, what's the prescript, in this case, installation of some Python package. This is a very straightforward example. And then you're going to leverage the distributed args by using the environment variables that are implicitly defined by PyTorch job in this case, because we're using an elastic torch run. And then essentially your command is a torch run, and then you pass the args and you launch the job. So that's what your YAML file, the values file, that looks like. And of course, you want to use this with a chart. So that chart that you want to use it with is going to define the PyTorch job, the config map, and all that using these values files. And the pipeline for this is going to look like this. This is a Kubeflow notebook running inside, and I'm accessing it from a Kubeflow dashboard. And so in this context, I am essentially connecting with the Kubeflow pipeline as a client, and then I get the namespace that I'm in, and then I define my Helm chart config, the JSON for it, and give it a release, just like you would with Helm Anywhere. What namespace you want to release in it, where is the repo URL for the chart you want to use, what is the path to the chart, and then you basically essentially read in the YAML values file that we just saw, and that basically defines the Helm config. In this case, it's very simple. There's only one, and then you define a standard experiment in Kubeflow. You create the experiment, and in this case, you create a pipeline from the pipeline package that we just talked about, which essentially operates on an input of a list of these chart configs. In this case, there's only one chart config that we are giving it, and it basically then runs that. So if you look into the Kubeflow dashboard, this is sort of like what that experiment looks like. And then, of course, you could go to a run within the experiment. And then, of course, you can look at the logs, and you can look at the details of how it was defined, what was the Helm chart config, and the logs will tell you what happened and so on. So now let's look at a slightly more complex example, or significantly more complex example. So let's say we wanted to use that NeMo-Megatron framework, and we want to fine-tune a Llama 3.818B model, do PEFT LoRa fine-tuning with that Dolphin data set. Now, in this case, we have a number of steps. So first of all, for each of these steps, we're going to have a YAML file because we're going to use a chart and a YAML file for each step. So what does the pipeline for this look like? So there's the standard boilerplate that we saw earlier. In this case, the image is not standardized. We build a custom image, so we allow for that. And so you can inject that. We are dealing with a gated model, so we define a Hugging Face token to be able to access the gated model. And our first config is to just download the weights of the Hugging Face model. And so that's what we define here. And the chart we use for that is called Hugging Face snapshot. This chart basically just snapshots the Hugging Face model and stores it locally. And locally basically means on a persistent volume claim like an FSX Luster or an EFS in the context of AWS. And so this is what this download config chart config does. Then the next step is defining the chart for converting the Hugging Face checkpoint to NeMo. And it uses the YAML file it needs. Then the third step is for essentially pre-processing the Dolphin dataset from the Hugging Face dataset format to the one that NeMo understands. Again, another YAML file that basically defines that. And we'll take a quick look at these YAML files in a second. And then you do the fine-tuning, the actual fine-tuning. So this is the one that's going to actually do the tuning. Then you do the evaluation. Then you merge the model, the PEFT weights into the base model, and then you convert it back to the Hugging Face checkpoint so that if you want, you can upload it. So now in this case, when you define an experiment, just like we did before, when we define the pipeline has these number of chart configs instead of just one. And but otherwise, conceptually, it works the same way. So again, you do the same thing. You run the experiment, and in this case, of course, in the run you will have the pieces that go inside it, and so on. Now, in order to access, if you want to access the underlying, each jobs runs and so on, in the solution that we are going to share the QR code with for the GitHub, and I also posted in the chat, is the idea is that we actually use these persistent volume claims that are shared between these Kubeflow notebooks and also the actual jobs that are going to run on the cluster. So in other words, you can actually directly from your machine, you can go and you can access the logs. So for example, the first job that we were talking about, I can go here and look at the release name of that. And then I can go under logs and I can directly access and see what happened there in terms of when that job ran. So this is the pre-trained log, right? So it basically ran to completion and gives me the accuracy, the F1 and so on. So this sharing of persistent volume claims between the actual running of the job and the running that we are talking about here gives considerable flexibility in accessing the information of the jobs that you are running this way. So that is it, what we wanted to share today. And let me go and share the QR code by sharing the PowerPoint screen. So you can have that information. And that's the GitHub, where you will find lots and lots of examples and more details about how to set up this environment and try it yourself. So that's it. Thank you so much.
This was great, fantastic. Thank you so much for presenting with us today. There is a question on the chat from Andre. If you have time to answer, since we need to move to the closing remarks. But this was amazing. Thank you so much for presenting. It was a very comprehensive session, so appreciate it.
Sure. So if we are talking about using multiple training config files and training scripts and so on, they can be templatized into the that config map that we talked about using the YAML file. If that is not something that you want to do, then all you have to do is basically just either break that step into multiple steps or use a GitHub to include those files. And then the rest of the files can come from the GitHub. You are still able to use a shared file system if you want to, but we have working across literally hundreds of examples, we have not found this to be a limitation because each step is doing something really simple. And so this has not been a practical limitation.
Fantastic. Well, thank you so much. And thank you for sharing the link. Actually, I was wondering about where we can access the source code. And yeah, it was amazing. So thank you so much.